Alright, this video is produced to talk about Le Chatelier's principle, and today I'm going to be working on a tablet, and I can't really see what I'm drawing other than what I see on the screen above me, so that's going to make it a little harder to write. So today we're going to talk about Le Chatelier's principle. Le Chatelier's principle is generally covered after we've talked about equilibrium, and we've talked about ice tables, initial change in equilibrium type problems, and we've discussed equilibrium constants. Le Chatelier's principle starts with a system being at equilibrium. And when we apply a stress to that system, the system becomes out of equilibrium, and the system will shift in such a way as to relieve that stress. And a lot of times when we talk about Le Chatelier's principle, we like to bring in a physical type equilibrium like a seesaw. So here we have the board and the fulcrum of the seesaw, and we're at equilibrium. And so if we add a extra weight to this side of the seesaw, that's a stress, and that stress forces the seesaw out of equilibrium. So we get this diagram. So Le Chatelier's principle says the system will shift in such a way as to relieve that stress. So what happens is some of the weight has to be transferred over to the other side. And when we do that, we will eventually reach equilibrium again. So the seesaw analogy helps us to visualize what's happening in a chemical reaction. So let's start with the reaction, a simple one, A going to B. And we'll put our double-headed arrows here since it's reversible. Alright, so we have a balanced equation. The first thing you should do when you're talking about Le Chatelier's principle is write an equilibrium expression. This is the equilibrium constant, which is equal to the concentration of B over A. If we were talking in terms of gases, we could call this equilibrium constant at pressure. With respect to pressure equals the pressure of B over the pressure of A. Alright, so theoretically, let's say that the equilibrium constant is equal to 4 at 25 degrees Celsius, and we already at equilibrium, so K equals 4, and let's say that the concentration of B is 8 molar and the concentration of A is 2 molar. So 8 divided by 2 would give us 4. Now remember here too, there is an infinite number of possibilities that B and A can be that will give us the value 4. Maybe this is 16 divided by 4. I'm usually using whole numbers, but think about there's an infinite number of numbers that when we divide one by the other, we will get the number 4. Alright, so in this system, if I increase the amount of A, so I add some more A, add A, oops, it's not the best A there, right? Add A. Well, what does that look like on the seesaw? Well, the seesaw was balanced and now it's out of balance because we got too much reactant. Maybe A goes up to 8. And 8 divided by 8 would be 1. So let's just say that's what happens. Okay, so K is 4. And over on this side, we now have 8 molar B and 8 molar A. Now, once we've changed this is no longer the equilibrium, right? So what we have to do is bring in a new term called the reaction quotient, which is Q. The reaction quotient is used when we're dealing with non-equilibrium conditions. So what we have here is we have the 8 molar that we originally had of B, but now we have the 8 molar concentration of A, and so Q is equal to 1. Now when we compare Q to the equilibrium constant K, which is 4, we see that Q, the reaction quotient, is less than K. K being 4, Q being 1. So when Q is less than K, the reaction will always move in a forward direction. So we say forward. You also hear the word to the right. Or to the products. All right. Let's move on to another slide. Well, before we move on, again, what happens here? Yeah, let's go on and finish this out. So A, we have more A than B, and that ratio is less than this number 4 here. So what has to happen is the reaction A has to be reacted to form more B until the ratio of A and or B and A comes back to the number 4, the equilibrium constant. So this is one way we can exploit chemistry, in that if we're trying to make a product B that we're trying to sell, well, one of the ways we can make more B is by adding lots of A at the beginning of the reaction. Keep adding, even once we reach equilibrium, add more A to force the reaction to make more product. All right, let's continue on with this. Let's say, let me get the pen here. So we have, again, A going to B, and again the equilibrium expression B over A. So another way we can create more B is, let's say we're back at equilibrium. We could remove B. So here's A on this side, B on this side. We remove some B, so that makes, again, the same situation where we've got a stress on the system. We've got too much A and not enough B. It'd be kind of like, maybe here this is K equals, well, let's do this. Since we're out of equilibrium now, let's erase that and call it Q. So we have Q equals the concentration of B, let's say, is now 4 molar, and the concentration of A is I don't know, 2 molar. All right. A lot of times we don't use if we're talking about Q, we don't use brackets. We'll use parentheses to say, hey, we're not at equilibrium. So we have something like this. So Q would be equal to 2, and Q again would be less than K, and this reaction would have to shift to the right until we get back to a ratio here that would equal 4. All right. So what I've shown here is the relationship between K and Q, and how when we have a system at equilibrium and we apply stress by either adding A or taking away B, we will have a system where we are out of equilibrium, and calculating the reaction quotient, the quotient will be less than K, and the reaction will have to shift to the right or to the products or in a forward direction to get back to where the reaction quotient is equal to K, back to equilibrium. All right, there is other parts of Le Chatelier's principle. We can think about the relationship of pressure on equilibrium. So let's say we have A, let's stick with the same theme, A going to B. And let's say these are both gases. All right, and let's talk about this one in terms of Kp. So this would be the pressure of B over the pressure of A. Okay, how can we relate concentration and pressure? Well, we've seen it before. We saw where Kp equals Kc times RT delta N, where delta N is the change in the number of moles of gas from the reactant side to the product side. In this case, there is no change in the number of moles of gas, and so Kp equals Kc, because RT raised to the 0 power is 1. R is the gas constant and T is the temperature. So, in the case of this reaction, if we have a cylinder here, and we're going to represent the pressure as a piston. That's what this is. This is my piston in the cylinder. And that's the way we draw things in chemistry and physics, is that we're not always saying we're working with a piston. It's just a way for us to symbolize the pressure over a reactant or system. So we have A and B in here, and we're at equilibrium. And so we decrease the pressure. We increase the pressure by moving the piston down. So now the piston's down here, and now A and B are in closer proximity. And so what does that do? What kind of problem does this cause? Well, think about the relationship of pressure and concentration. If you go back thinking about ideal gases, PV equals nRT. If we solve for P, we get P equals N over V RT. And notice this looks a lot like moles per liter. So there's the relationship. And that's why we have this correction factor up here. All right. Now, tell me what happened here. The pressure went up. The pressure went up because we've decreased the volume. The volume went down, so we're seeing that inverse relationship between pressure and volume. What about the number of moles? Well, they remain constant, right? And is A and B's volume affected the same amount? Well, think about it this way. If we write this Kc equals N over V of B, so there's the molarity of B, and we divide that by N over V, that's the molarity of A, and the moles stayed the same, and the volumes changed the same amount. Is there any effect? Think about it. No, there's no effect. Both things are affected equally. So in the case of this reaction, if we are at equilibrium and we apply pressure by decreasing the volume, there's no effect on equilibrium. Let's look at a different system. Let's say that A is going to 2B, and both of these are gases. All right, so we write the equilibrium expression with respect to pressure here. We get pressure of B squared, because of the coefficient in front of the B, divided by the pressure of A. And we could also write that in terms of N over V, B squared, and N over V A. All right. So we're running out of time, and I'll pick up on this video in the next video labeled Le Chatelier's Principle 2.